The program at this point turns from microelectronics technologies, computer evolution, to energy and power conservation. And I can't tell you how interested I am in listening to our speakers predict what will happen in that field in the next 100 years. I can't even project what's going to happen tomorrow in my company, and just to be able to get a few years down the road and crystal ball gazing is something that I would certainly dearly love to achieve. Our speaker this morning is Dr. R. David Middlebrook. He is professor of electrical engineering at the California Institute of Technology and is a fellow of the IEEE. His publications include numerous papers, a book on solid-state device theory, and another on differential amplifiers. His research interests, formerly in solid-state device modeling, now in circuits and systems, and particularly in power processing electronics, in which he is well known as an author, lecturer, and consultant. He is the recipient of the 1982 IEEE William E. Newell Power Electronics Award for Outstanding Achievement in Power Electronics, and a 1982 Award for Excellence in Teaching presented by the Board of Directors of the Associated Students of Caltech. He is especially interested in design-oriented circuit analysis and measurement techniques, which he teaches at Caltech, and has conducted short courses on his methods in both Europe and the United States. Among his outside interests is Formula race car driving, which makes him certainly an well-rounded individual. It's a pleasure to present Dr. Middlebrook.
Thank you. We've heard quite a lot about power already in this day and a half of the Convocation, but it's all a matter of definition, because the kind of power we've heard about is computing power. And definition, of course, is everything. It's like giving a definition of when life begins is when the egg is fertilized, but definition I like better is that life begins when the kids leave home and the dog dies. Well, power also has many definitions, and computing power is certainly one of them. I'm going to talk about a different kind of power, but probably even yet a different kind of power from what you probably expect I'm going to talk about, which is perhaps a little odd too, considering that we're celebrating 100 years of the IEEE, which began as the AIEE, whose principal concern in the early days was power, and the IRE came along a little later. But the kind of power that I want to talk about under the heading of power processing is not power generation and distribution, but changing power from one form to another, subject to important constraints. And I want to do this under the guidelines of comparing and contrasting power processing with signal processing. You can have the first slide, please. There are some similarities between these two fields, and in fact, we purposely like to use the terminology of power processing in order to point out the similarity with signal processing. In the signal processing system, the important quantity that you want to preserve in going through the system is the information content. That's what's important. Now, we perform certain functions on that signal, and typical functions are analog amplification, or digital recoding, or A to D conversion, or D to A conversion. Those are generalized functions of signal processing. It takes a little bit of power to accomplish that, and one of the objectives of modern signal processing electronics is to minimize the amount of power it takes. Now, in contrast to that, in a power processing system, The two inputs now get interchanged. The power is what you want to preserve. The energy is what you want to preserve in going through the system, even though you perform various functions on it. Typical power processing functions are DC to DC conversion, AC to AC cycloinversion, DC to AC inversion, AC to DC rectification. Again, that accommodates most of the functions that we want to consider in processing power. Notice the information content now is the control. And the constraint in power processing is overall efficiency. Since we don't want to lose any of the energy in going through the system, this is the same thing as saying we'd like to do the processing ideally with 100% efficiency. Of course, that isn't going to happen in practice. And if the efficiency is eta, then 1 minus eta is the fraction of the power lost, which is exactly the same thing as the epsilon that Dr. Frosch was talking about yesterday. That's the difference between the ideal objective and what you can really do. And that's the important part. That makes the difference as to whether you're going to get the system to work or not. You have to allow for that epsilon. And in the case of power processing, again, the objective is to make the epsilon as small as possible, but you have to account for it, and that really determines, to first order, what the system is going to be and how you're going to put it together. And that's the objective of power processing, is how to put together the right elements to achieve the desired function. Now, power, in a sense, began as an engineering discipline with Faraday when he discovered that if you moved a conductor in a magnetic field, that an EMF was induced. And in fact, there's an exhibit you may have seen in the hall here which allows you to do that, and not only to generate the EMF, but to determine that when you load the system, that it takes more mechanical effort to move the wire. That was one of the foundations of electrical energy generation and use in electric motors, for example. Also, interestingly though, signal processing began in the very early days, also with the telegraph. And in fact, Dr. Lucky yesterday had two very nice slides, which I would like to borrow. He had the human aspect of it. I have the technical aspect of it. This was the one that he showed to do with the poles with all the dozens of wires hung on them. And the principle is that you simply turn on and off an electric current and detect whether it's on or off. And this is digital signal processing. And this was developed to a large extent. And if the switch is turned on in one circuit, then this propagates now to the power in another circuit which can be detected. And so the information is transmitted as to whether the electric current is on or off in the initial circuit. Sometime after that, analog signal processing was developed, and again, Dr. Lucky had the telephone switchboard to illustrate that, and I have the analog signal circuit. This is analog signal processing, and essentially took over in signal processing for very many years after that. This led ultimately, through the days of the vacuum tube, to the semiconductor, the junction transistor, as we know it now, as a device, which can always be used in two modes of operation, either as an analog amplifier or as a digital amplifier. And you can convert one to the other simply by increasing the amplitude of the signal that you drive it with until it overloads, and so the output simply crashes back and forth between an off condition and an on condition, and that generates the digital signal. This is a very early transistor, a junction transistor, whose structure physically was similar to the picture that I just showed. Now, jumping over a number of years that we've heard a lot about, this is an integrated circuit stolen from Carver Mead's book, and this is the kind of picture that you've seen many times. Other devices were developed for use in power processing. There's a power transistor up at the top shown as a digital amplifier, and a silicon-controlled rectifier, which can be turned on but can't be turned off again by the control input. It can only be turned off by removing the source of power. This is a picture of a relatively large-sized device, actually some diodes, to indicate that this is simply a larger physical structure, and the reason for the larger physical structure from the signal processing device is to get rid of the heat. That's the epsilon, and if the amount of power you're trying to process is large, then even epsilon gets large, and you have to do something about it in the form of a relatively large heat sink. Now, when we're talking about how you design power processing circuits as distinct from signal processing circuits, all design engineers have the same basic elements to work with, namely resistors, inductors, capacitors, and the active devices, semiconductors nowadays, which can be used in two modes of operation, in the linear or analog mode or in the digital or switching mode. These are typical discrete components that represent the use of the implementation of those components that we use in circuits. And in signal processing circuits, design engineers are perfectly willing to use all of those components, except that they hate magnetics. Magnetic devices don't fit onto the ICs very nicely. They're totally incompatible in physical structure with the extreme degree of miniaturization which we can accomplish now in ICs, integrated circuits, LSI and VLSI and so on. In fact, signal processing design engineers will go to great lengths to avoid using any magnetics, even if they should need the function of an inductor. And you can simulate an inductance by a bunch of operational amplifiers and integrated resistors and capacitors. And that's all very well, but you have to remember that what you're simulating is L di by dt. You're not simulating a half Li squared, which is the energy storage property of the inductor. You can't do that with your op amps and integrated components. And for that reason, the design engineers who work with power processing circuits have a different selection of components that they can work with. This time, they hate resistors, because resistors are lossy, and that doesn't meet the requirement for ideally 100% efficiency. So power processing designers will go out of their way to minimize parasitic resistance. And for the same reason, they also have to banish the use of analog or linear devices. You can only use switches. So it turns out that right from the fundamental point of view, that when you start designing power processing circuits, you have different pieces to put together into the jigsaw puzzle that's going to generate the final picture. And there's a basic conflict involved in that also of interest to the design engineers themselves, and that is that if you have to work solely with energy storage elements, the inductors and capacitors and switches, and you try to minimize the losses as much as possible because of the efficiency objective, then you know that what you're going to get is very high resonances, very high Qs of tank circuits. And it's sometimes difficult to accommodate those big resonances in the system design, but that's a conflict that exists, and it has to be recognized in the design of the system. Now, some of the things that you do with power processing circuits provide regulated power supplies, which is needed to power all of the equipment that we hear about. The conventional way of doing that used to be that you'd use a 60 hertz transformer to step down the input voltage to some low level, 6, 7, 8 volts, and then you rectify it to DC, and then you'd put in a so-called linear regulator to drop the voltage down to the required 5 volts or whatever, and that works perfectly well as long as you aren't transmitting very much power. But if you load it, then that load current has to go through that series element, and that results in power dissipation, which results in turn in having to build a large heat sink and possibly use forced air cooling. But that was the conventional way of building a power supply, and there was nothing very difficult about that. Any electronic engineer could do that as part of this overall system design, and in fact he did do it. The fellow who was designing the entire system would automatically be expected to design the power supply at the same time. Now, this was all right in the days when a computer, for example, the big mainframe, took up most of the room, and it didn't matter whether you had these big linear power supplies with the 60 hertz transformers and the heat sinks and the forced air cooling, because in proportion that was all right. The problem arises that with the tremendous strides in miniaturization with LSI and so on, the signal processing part of it shrank smaller and smaller, and the power supply stayed big because no one paid any attention to it. And it became then totally out of proportion with the whole system. So a different means of achieving the power processing function had to be used. And since we're only allowed to use energy storage elements and switches, and since transformers don't work at DC, if you do want to transform DC from one level to another, then the first thing you need to do is chop it up and make it into AC. And so the principle is that you have a switch you can put right at the front end to alternately connect an output to an input and disconnect it. And you have a low-pass filter because you don't want that switching frequency to appear in the output. You want only the DC average value. And so by this means, you can convert DC from the peak value of that square wave, which is the input, to the average value, which is a lower value. And furthermore, the regulation function comes for free, because simply by adjusting the fraction of the time that the switch is in that top position, if you make it in the top position longer, then the average value is higher, and so the output is higher, and so on. So there's a continuous gradation now which allows you to control the output and achieve one of the other important functions of power processing, which is not only the conversion of the power itself, but the adjustability of the conversion ratio. And you need that adjustability to be electronically controllable, because usually you do want to regulate the output, and so you have to give the system some function to operate on. So as a result of that now, the modern way of achieving DC to DC conversion, for example, the 110 rectified input down to the 5 volt, is that you now rectify at the high voltage end, and then put the switch immediately after that, and operate the switch at a high frequency. Now it's 20 kilohertz at least and on up, instead of the 60 hertz. So now you can transform down with a much smaller physical transformer at the high frequency than you could at the 60 hertz frequency. And since you get this regulation function almost for free, then that is the final step in the output. So this particular kind of power supply is known as an offline switcher. And this is the modern way of achieving power conversion, with the result that you can now make it much smaller. First, because the transformer is smaller, operating at higher frequency, and second, because you have much less heat to dissipate for a given amount of power throughput. So now the power supply is of a size, again, compatible with the rest of the system. Now, there are many kinds of power converter, and it's convenient to classify them with respect to the quadrant of their output. And a one-quadrant output is a supply that provides one polarity of voltage and one direction of current. So it's a unidirectional power flow. There's a number of obvious applications of that kind of power supply. It includes all type lab power supplies and most power supplies that are used to power the electronic equipment that we're all familiar with. Here's a typical example of the state-of-the-art of that kind of power system. This is a multiple output offline switcher of the kind that I just showed the diagram. And that is used in desktop terminals and computers, word processors, and so on. That's the typical application for that kind of power supply. Now, where are we going in the future with this? Well, power supplies are going to become more integrated, just as the signal processing systems have been. And one step along the way of the integrated power supply is that can in the middle, which you would normally think consisted of only the power transistor, this particular one has some of the control circuitry in it as well, the driver and the control for the power transistor. You notice that the other components are still discrete, they're still outside that integrated circuit. That's because we have to work with these large energy storage elements, the L's and C's. But this is one step along the way. The whole thing can be packaged into a pretty small space. This is only a 25-watt regulated power supply, but we can do better than that already. The next generation is going to be still using discrete components, but surface mounted on ceramic substrates and essentially getting rid of the individual package for each component. And one requirement for being able to do that is to do the switching function at much higher frequencies. Now, this is a 25 watt power supply also that operates at 300 kilohertz switching rate. And as a result, the magnetics and the capacitors are much smaller than they were down at the 20 kilohertz frequency, which is what the previous module was switching at. Another generation, a similar kind of thing, also showing some relatively small magnetics. So this is only about a 10 watt power supply. But there's going to be further strides in this in the very near future. The integrated circuit slide that I showed earlier is sort of the obligatory slide that everyone has to show, which we already heard before, to show what ICs look like. This one doesn't look much different, except that this is a single device now, which is really put together from a large number of very small discrete devices, and the difference is in the connections, because in the typical integrated circuit, the connections are to a large degree serial, but in this device, the connections are parallel. All these individual little squares, each of them is one device. All we do is connect them in parallel, and it makes effectively a large power device. So the next generation of power supply is going to look more like that. Now, everything is in there, and it's operating, of course, at a high switching frequency. The next thing that's going to be different in this field is that we're going to have decentralized power processing. Instead of having one power supply for the whole word processor system, or whatever it is now going to be economical to have distributed power processing, and the isolation and the noise requirements will typically be met by the central power supply, and then there'll be an internal bus, so at some lower voltage, probably less than 50 volts because of certain safety regulations, and then there'll be local regulation that occurs on integrated circuits distributed throughout the system. Now, all of these that I've illustrated so far are one quadrant output type of systems. The next most complicated system is a two quadrant output. In this particular case, I've shown one polarity of voltage, but now two directions of current flow, either direction of current flow, which means the power flow can reverse. Applications for this kind of power processor would be battery chargers and dischargers, and DC motor controllers. A DC motor controller doesn't necessarily have to be a two-quadrant processor, but it's convenient if it is, because then you can recover some of the kinetic energy of motion of the vehicle and put it back into the batteries again. There's an electric car represented by the entry into the Caltech MIT electric car race of 1968. And it's the desirability of having a bidirectional processor seen when you look at the batteries. And remember that an electric vehicle is 2 tons of lead on wheels, and it takes an awful lot of stopping. And even though you don't get that much energy back into the battery, the fact that it gives a braking effect is really more important than the energy recovery. And another problem which is really limiting the application of electric vehicles now, of course, is not the power processor itself. It's simply the energy source itself in the form of the battery or a fuel cell. This is volumetrically just not competitive with the fossil fuel engines at the moment, largely because in a gasoline engine, for example, the reason that you have such a small fuel tank is that 90% of the fuel you're not carrying with you. That's the air. You're only carrying 10% of it. And of course, with other types of source, such as the battery, you have to carry all of it. That means that you have to have a big socket to plug it into. And in that electric car race that I referred to, they actually did this. They arranged with a local utility to plug into one of the distribution transformers along the way and get that battery pumped up again. Finally, there are 4-quadrant power processing systems. This means that since you can have both polarities of output voltage independently of both directions of output current, the information input to the system can now be used to tell the processor to convert DC into AC. And this is the most general form of output. One application for this, which is still in its infancy, is solar array photovoltaic conversion, where you have a rather variable DC now, which you need to convert to AC to parallel with the grid or to operate household appliances. This is an example of a DC to AC inverter for that purpose. This is a 4 kilowatt unit. This is not economically feasible yet because of the cost of the solar array. Again, it's the energy source which is the limiting factor and not the processor. Other examples of waveform processing that we can do, this is a simple phase control rectifier, the kind that you have in your wall switch that dims the lights. In larger sizes, this is used on the New York-Washington Metroliner train also. This is an example of cyclo conversion, where you change one frequency to another directly without going through an intermediate DC link. And here's another method of generating AC by pulse width modulation, where you essentially generate a sine waveform. Now, 4-quadrant outputs are useful not only for solar array inversion, but for induction motor control. This is a DC to 3-phase controller of about 1 horsepower level as a feasibility model. And this will be a tremendous economic advantage in all the applications where you want to have variable speed of an AC motor, because it's been known for a very long time that of all the electric motor types, the DC motor is the heaviest, most expensive, least reliable electric motor there is, and an AC induction motor is the opposite. For any given power rating, it's the smallest, cheapest, most reliable motor. And the trouble is that if you feed it with a fixed frequency, it goes at a fixed speed. And it's very difficult to vary the speed of an induction motor mechanically. But if you can control the frequency of the power that you feed to it, then you have complete control over the speed of the motor, and this will be a tremendous advantage not only for traction, but for all industrial applications, in particular pumping of fluids. Now, if you can make a DC to AC inverter to operate from 0 up to 60 hertz or 0 up to 400 hertz, then you have that range of application, which can go to quite high powers. If you work a little harder and make the bandwidth from 0 frequency to, say, 20 kilohertz, then the reference information input to the power processor need no longer be a pure sine wave. It could be an audio signal, which means that you've now built yourself a switched mode audio amplifier, which is ideally 100% efficient, which is much better than the 50% efficiency of Class A and the 68% efficiency of the standard Class B. This is an example of a 2-channel stereo switching amplifier where the switching frequency is 0.5 megahertz. Now, this again is simply a feasibility kind of model. This kind of amplifier isn't going to win any prizes in the stereo hi-fi market, where every amplifier data sheet has to say the distortion is 0.001% or something from 0 to 100 kilohertz, whether you need it or not. That specmanship requires that you have to put that on the data sheet. So switch mode amplifiers won't make much headway there, but they might do a little better in applications where you need a lot of audio power and you can stand a little more distortion, such as public address systems. And of course, rock bands would think they're just great. And if there isn't enough distortion in the amplifier, they'd be glad to add some more to it. Well, I can't resist ending with some remarks about the educational aspect of power processing. Power sort of fell into a backwater in academic circles, at least in this country, after World War II, and all the emphasis was put onto electronics, And it was the thing to do in those days was to study applied physics. That sounded even better than electrical engineering, because everything was supposed to have been done in electrical engineering. And when we have modern students now who don't even want to be analog engineers, they all become instant digital nuts as soon as they take their first computer course. In fact, this is so extreme that sometimes I think we turn out graduate engineers who think that what goes down wires is ones and zeros. But as industry well knows, it's hard enough to find any graduate engineer who's even interested in analog, never mind power. And we've tried very hard to do something about that in recent years. And one of the things I found very quickly I had to do in talking to students was never to use the word power supply, because obviously power supplies by definition must be dull and boring, and no one would want to bother with those. So I very quickly learned to use the term switched mode energy conversion, which sounds a whole lot better. But what it really comes down to is that the things that this slide says are really fundamental to generating interest in students nowadays, because when you tell them that in fact switch mode power conversion is a considerable technical challenge, then you can get their interest. And that's absolutely true, because to be a specialist in switch mode power conversion systems, you have to know not only digital and analog signal electronics, you have to know not only linear and nonlinear control systems, but you also have to know about magnetics, something that no student has ever thought of for years and years. You're lucky if you find an engineer now who knows that a transformer is N1 to N2. Never mind anything to do with how you choose the core or the number of turns. So magnetics has been a closed book for many generations of students too, and we need to try to do something about that. So when you put all those together and try to make the point that to be a power engineer in modern terms, you actually have to be a specialist in quite a number of these disciplines, then things begin to look a little better. At Caltech, we've been working for almost 15 years now to do that, with some considerable internal success, because there's been a complete turnaround from the early days when I had to drag the students in through the door, kicking and screaming, to what the position is now, where we have some of the best students who come knocking on the door trying to get in. This is very encouraging, but the unfortunate fact is that there are still but a handful of universities in this country who have any kind of instructional, never mind research program in switch mode power conversion. And we're going to need quite a lot more of those in the future, and there are some very challenging topics to be dealt with now. And as I mentioned, the next generation of power processing is going to go integrated in the same sense that the signal processing did, but there are a lot of new problems to be solved there, particularly what to do with the magnetics in order to make them compatible with the signal processing system. Well, I'll end there and turn over now to John Kassakian to talk about some other aspects of power processing. Thank you.
Thank you, Dr. Middlebrook. To discuss this paper and amplify the topic a bit, we're happy to present Dr. John G. Kassakian. Dr. Kassakian is Professor of Electrical Engineering at the Massachusetts Institute of Technology. He received his BS and MS degrees in Electrical Engineering from MIT, as well as his Doctor of Science after a tour duty in the U.S. Navy. The focus of Professor Kassakian's research has been energy conversion and control using power semiconductor devices. He has placed particular emphasis on understanding and overcoming obstacles to the more effective and extensive application of this technology, especially at very high frequency. Professor Kassakian is a member Senior member of IEEE, member of Tau Beta Pi, Eta Kappa Nu, and Sigma Xi. It's a pleasure to call on Dr. Kassakian.
Mr. Chairman, ladies and gentlemen, colleagues, it's a privilege and an honor to be in such distinguished company this morning. And as I've listened to the talk of the challenges we face, particularly with respect to biological systems, I'm reminded of a remark that was made by Dr. Hans Lucas Teuber, who used to head the psychology department at MIT. He used to teach the introductory psychology course on campus, and it was extraordinarily popular. He said, science, with all its wisdom, never been able to reproduce human brain. But unskilled labor is mass producing them. And I think that the challenges we face in that regard are something which the second century probably not going to allow us to achieve. But there are some challenges which perhaps are a little more attainable. And I submit one of them to you, and that is that somebody design a damn badge that doesn't twist. Now, instead of commenting specifically on the points which David has made this morning, I'd like to take this opportunity to share with you some observations regarding our energy use patterns, and in particular, their implications for our second century. There's no doubt that we've become an energy-conscious society, and the economics of energy is largely responsible. However, our changing patterns of energy use have been driven by much more than economics. In 1970, I used to buy gas for my BMW 2002 at a Clark station in Minneapolis that sold nothing but leaded premium, and that at 35 cents a gallon. Gasoline now costs about $1.35 a gallon. That's economics. You couldn't find leaded premium today if your life depended on it. That's the environment. And BMW no longer makes a 2002. And like Dr. Kaufman's 55 Chevy, that's a shame. But whatever the reasons, the numbers support the fact that we as a society are using less energy. And this while the GNP continues to grow. Judy, can I have the first foil, please? I show here the GNP since 1950 in constant dollars. And depending upon whether you're for Reagan or Mondale, you might fit that curve differently to the points. But nevertheless, it would be difficult to interpret that data as anything but an increasing GNP. Of more interest to us, however, is the energy used to generate each dollar of GNP. And we see here, shown in detail for the last decade to illustrate its small scatter, that after 2 decades of a nearly constant 60,000 BTU per dollar of GNP, the behavior of this parameter for the last decade is startling. An explanation which comes easily is energy crisis and conservation. But I believe the real reasons are far more complex and have major significance for our second century. Indeed, one could compellingly argue that from a structural point of view, our second century began in 1974. An even more interesting trend is the electric energy content of each BTU. In the next foil. In 1950, 3% of each BTU of energy consumed was electrical. By '83, it had risen to 10.5%. While total energy use declined by 5% during the last decade, electric energy use increased by 25% during the same period. And while total industrial energy use declined by 18%, industrial electric energy use increased by 12.5% over the same 10 years. You can turn those off. For certain, these statistics reflect in large measure the decline of some of our mature heavy industries, a decline which one might compellingly argue was inevitable and not a product of the energy crisis. But what these data also reflect is an increasing demand for high-quality energy, for energy that can be controlled precisely and squirted where we want it. Last night, before the banquet, I was watching a Channel 3 news broadcast of yesterday's Centennial events. It also included shots of some of the Institute's exhibits. It also included some of you. A 7-year-old boy was marveling over what the Van de Graaff generator was doing to his hair. The reporter asked him what was causing this phenomenon. Electricity, he answered. What is electricity, she asked. His response was, I'm not sure, but it's very powerful and it can do almost anything. Now, some may argue that he's getting a poor education, but the little fellow's very observant. And the fact that it can do almost anything is why demand for electricity will continue to grow. This demand, of course, has been created by the availability of components and processes made possible by the technologies we've been discussing this morning. Technologies which are producing a dramatic and fundamental change in the structure of electric energy demand. An integral part of these new electric loads is the power electronic circuit that both forms and squirts the energy. Dave has just given us a fascinating introduction to power electronics. Let me give you another example of the role which such circuits can play, even in relatively mundane applications. Could I have the first slide, please? This slide shows a conventional single-phase full-wave rectifier operating at a power level of 4 kilowatts. The traces on the bottom in the photograph, the top trace is the AC line voltage and the lower trace is the AC line current. The peak energy storage in this circuit, of course, on the DC side. Beg your pardon? The peak energy storage in this circuit is approximately 170 joules. Now, this figure can be translated into pounds of iron and copper or cubic inches of mylar. The AC line current is rich in harmonics, has a high ratio of RMS to fundamental, and a poor power factor. Harmonics cause interference, and a poor power factor loads the line unnecessarily. What you see here in the line current is typical of the line current in your TV or PC. In fact, what you see here is probably somewhat better. See the next slide, please. This next slide shows the addition of a high-frequency modulating stage, which creates the sinusoidal line current shown in the lower trace in the photograph. The transistor is switching at 20 kilohertz. It's controlled by a microprocessor using a switching pattern stored in RAM. Although the circuit has been complicated, the total energy storage is only 17 joules. That's 1/10 of the energy storage in the previous circuit. The quality of the DC, although not shown in these slides, is 10 dB better. And the response time of this circuit in a control loop is 10 times faster. Okay, you can turn that off. I believe that the increasing demand for electric energy is being driven and will continue to be driven by applications made possible in part by power electronics. It's significant that the first 6-inch wafer fab facility in Silicon Valley is initially intended not for VLSI, but for the fabrication of power devices. It is also my opinion that the changing nature of the electric load will have a significant and challenging effect on the electric utility industry. Power engineering is going to have a new identity in the century ahead. Thank you.
Thank you, Dr. Kassakian. If the two gentlemen will take their places, we'll take questions from the audience. Yes.
I wonder if Professor Kassakian could go a little further in delineating how this changing power electronics is going to change electric utility loads.
Would you give your name and affiliation, please, for the
My name is
court reporter? Please.
My name is Fetter, and I'm a consultant. Did you get the question?
Yes, I got the question.
Would you repeat it, please?
The question was, how is power electronics going to be changing the nature of the electric loads? I believe that was fairly, excuse me? I think that it was already alluded to in Professor Van Dam's comment that we're moving into an area of refined power. The idea of bulk power, while certainly it's still with us and will be with us for many decades, I think is going to be replaced in many places by a need for power of different quality, higher quality, higher reliability. Centers of load will be more distributed. And of course, the interface between the load and the utility will be very much electronic. And other than saying that, I don't want to predict what's going to happen, but certainly automated manufacturing, the integrity of power for information processing, all of these applications which we can see now are going to have a profound effect on the utility supply.
Another question.
My name is Irv Engelson. The IEEE started a new council on power electronics very recently. Dr. Middlebrook indicated a triangular distribution of the technical spectrum with electronics in one corner, power in another, control in the third, with the power electronics in the middle. Do you see this evolving into a square where power electronics will be one of the corners?
I tried to indicate that power electronics is an overlapping of those three general areas. It's the publication situation is in quite a mess, which is one of the reasons for the formation of this Power Electronics Council, and one of its principal objectives is to start a journal, which unfortunately isn't going to happen for a little while yet, but that was one of the main reasons for doing it, because the situation right now is that you don't know where to look for technical papers in this field. It's scattered all over the place.
Yes. Would you give your name and affiliation, please?
You expressed concern regarding the lack of this power supply educational programs in universities. And to get students interested in taking these kind of programs, there has to be a motivation, maybe see opportunities in industry. Can you cite any evidence of how the problem, this lack of educational program problem, is impacting industry?
Well, there's a very clear manifestation, which is that I get telephone calls several times a week from headhunters. asking who I can recommend that they could approach for a position in switch mode power. And 95% of the headhunters have no idea how hard a job they've got. Because the demand far exceeds the supply for people in this field.
We have time for perhaps 1 or 2 more questions. Seeing no hands up, I hope you've been as stimulated as I have by this rather far-ranging and fascinating conference this morning. I hope when the first humanoid is synthesized with the use of a computer, it will be programmed to feel hunger 3 times a day. We are due to break for lunch, and I know you will all join me in giving all of our speakers a well-deserved round of applause.
There's nothing on the schedule. I don't know.